Hi, everyone. Welcome to the SAEM Research Learning Series course online lecture titled Introduction to Clinical Data and Missing Research. It is my pleasure to introduce to you Dr. Rebecca Cash. Dr. Cash is an assistant professor of emergency medicine at Harvard Medical School and research staff at Massachusetts General Hospital. She is an epidemiologist and health services researcher who focuses on the emergency medical services workforce and pre-hospital care. Prior to joining MGH, she was an EMS research fellow at the National Registry of Emergency Medical Technicians, where she earned her PhD in epidemiology at the Ohio State University in 2019. She is also a nationally certified paramedic with about 8 years of experience working on an ambulance. Dr. Cash, I will now turn it over to you.
Thank you so much. I'm so excited to talk to you all today. I'm going to be discussing a problem that is commonly missing, pun completely intended, from some basic and general statistics classes. And that's the concept of missing data. So, when we're learning about statistics, we usually use these beautiful data sets. Everything is observed, and we don't have to worry about missing data. And that's really just not what happens in the real world. So I don't have any disclosures related to this presentation. And what we're going to talk about today are some basic terminology and major concepts of missing data. Hopefully, I'll be able to clarify some misconceptions that I commonly come across. I'm going to be discussing methods to handle missing data, all the way from basic things like complete case analysis to more advanced topics like multiple imputation. And then I'm going to illustrate some of those methods using an actual data set from NHANES, so that you can see visually what happens when we use some of these methods in the face of missing data. So before we jump into terminology, I want you to think back to the last study that you were involved in, or the last paper that you read. Try to remember, did that work have any challenges related to missing data? So whether you realize it at the time or not, it's a pretty safe bet to say that yes, there was missing data. In fact, in clinical research, missing data is really the rule rather than the exception. So, when we're dealing with human subjects, this just happens. Participants drop out of studies, they don't respond to a survey, or maybe they refuse a component of an exam, and therefore we get missing data. And that's okay. It's expected. The problem is, though, that missing the complete data methods that we're commonly taught are not always appropriate in the face of missing data. And so today we're going to talk a little bit more about how we can address and deal with missing data in a better way. So how does missing data happen? Like I said, non-response to a survey is a pretty common issue. So either someone doesn't respond to the whole survey, where we have unit non-response, or they miss an item or two, which is called item non-response. When we're following participants up over time, we can also lose them to follow up. So either they say they come to a baseline visit and then they don't come back, or they miss a study visit. Either of those results in missing data. Sometimes we actually purposely have missing data. We do this, by design. So say you have a large sample where you measure everyone for some measure, and then only a subset get, the second measurement done. Say, you ask everyone their weight and then only objectively measure weight in a small amount to validate the self-reported data, something like that. That's called missing by design. And then, stuff happens. So your dog, or, maybe a cat is probably more likely to do this, deletes your observations, your samples get contaminated, something happens, and then you have missing data. So you might be thinking that if it's so common, why should I even care, right? But the reality is that even small amounts of missing data can lead to biased results, which then leads to incorrect inferences, and that can end up with the wrong conclusion, essentially. And I peer review a lot, and I feel like most studies, hopefully inadvertently, but who knows, tend to use the default for statistical software methods when it comes to handling missing data, which is complete case methods. And with a complete case method, we are removing participants that are missing data, and therefore we're decreasing our sample size and our power. But we know that data collection is expensive. It costs time and money, and so we should be using our data to the maximum amount that we can. And then some of the common approaches that we frequently see are fraught with pitfalls, and you may or may not realize or appreciate the pitfalls that come with these, and therefore, there are better ways for us to handle missing data. So let's jump into some basic terminology. So first, we're going to describe missing data in a few ways, two being the missing data pattern, which values are missing, and then the missing data mechanism, which is why data are missing. So when we talk about missing data patterns, we can actually look at them graphically. And the most basic pattern is the univariate missing data pattern. So you can see that here. So where only one variable has missing. And if you sort your data set nicely, you'd see, there's the missing observations for that one variable. You can also have more than one variable missing. It's called multivariate missing data. In this case, we call this multivariate 2 because there's 2 missing. And in that, you see the same observations have missing data and the other ones are fully observed. Next is the monotone missing data pattern. So this is more commonly seen with longitudinal studies. So if you order and you sort your data, there's increasing missingness as you go across the variables. However, those 3 patterns, while common, are not the most common you'll see. Actually, the most common we generally see is this general or arbitrary missing data pattern. It's kind of like Swiss cheese. There's not really a way to order or sort these in a nice manner. You just sort of have holes all over. Next, we can have something called the file matching pattern. So this results from merging files that have a common variable, but the other variables don't actually match. And then finally, latent variables are essentially a missing data pattern. If you're not familiar with what a latent variable is, it's an unobserved variable. We can't actually measure this. We infer it from observed data, and therefore it is a missing data problem that we can analyze as such. So beyond describing the patterns, we also need to understand the mechanisms of the missing data. So why those data are missing. So there's 3 mechanisms we typically talk about: missing completely at random, MCAR, missing at random, MAR, and then not missing at random, NMAR, which sometimes also people call MNAR, depending on who you ask. So in my experience, there's a lot of confusion about the concept of MCAR versus MAR. So we're going to break each one of these down and hopefully clarify. So for missing completely at random data, we're saying that the probability of missing is unrelated to any of the variables under study. Could it be related to something? Possibly, but nothing that we're sort of interested in right in this study. So that means that the subset with missing data, or you can flip it around, the subset with observed data, are a simple random sample of this overall sample. And so if you're familiar with the concept of a simple random sample, they have very nice statistical properties that let us analyze things in an easier way than if it was slightly different. So this is the assumption that seems to be most often made. It's either made explicitly or seems to be more often an implied assumption. So without maybe realizing you're making this assumption, this is commonly what happens. But it's not always reasonable because, again, it has to be unrelated to any variable under study. We can partially test for this assumption by looking at the association between response or missingness and the variables of interest, but it's not a perfect test. And so it's, can't really go off of that. For all of these, what we have to go off of is really our own understanding and our reasoning to say this is what we think the mechanism could be. So let's give an example. So say we're sending a survey out to participants by snail mail. And so we shove those surveys in some envelopes, we put them in the mail, and some of those envelopes get lost in the mail and therefore they're not returned and they're missing. Or say we've collected some samples from participants, we sent them off to the lab, and a batch accidentally gets contaminated, rendering them now missing. Assuming that the surveys or the samples were not grouped in a meaningful way, right? We didn't just lose like a whole state of surveys, for example, we could say that this is a missing completely at random. What happened isn't related to what we're studying. As you can see, though, that's kind of a hard assumption to accept. Instead, it's more common that we have something called missing at random. So for MAR data, the probability of missing depends on some observed variable, but not the missing variables. So when we condition for these observed variables, like say we conditioned on like biological sex, and within men or within women, the subset that are missing are a simple random sample from that group. So you can see that's a more reasonable assumption. We can sort of, explain some of the reason why missing is happening with our observed variables. And in fact, most methods assume this mechanism, or they assume MCAR. MCAR is considered a special case of MAR. Now, we can't test this assumption. We can do the tests like I talked about for MCAR, but really we have to use our own reasoning to decide that this is the most plausible mechanism. So let's think of an example. So say we have that survey again, and on that survey, we're asking for the respondent's income. So the probability of reporting income then depends on the respondent's biological sex, which we know that's not missing. So then among men, the probability of missing is unrelated to income. It's a simple random sample of the men who reported their income, and the same thing among women. So as long as we condition on sex, missingness is dependent on that, we know that, which we have rather, then this is missing at random. So the next mechanism is not missing at random. And so for this, the probability of missing depends on the missing variable. So you can see that that would be a bit of a problem. We can't test this because what we need to test it is the thing that's missing. And we really, the only way we can determine that this is what's happening is to, again, use our reasoning and think through the problem and why people would or would not respond. If we use methods that assume missing at random, we can end up with biased estimates. And I'm going to actually show that later when we talk about some, applied examples. And therefore, they have actual specific methods that can handle not missing at random data, which we're going to briefly talk about. So let's think of an example here. So again, we have this survey, we've asked for respondents' income, and now the probability of reporting income depends on the income. So say those with a higher income are less likely to answer the question. So if we see something is missing, we can say then that the missingness is informative. It's telling us something. If the value is missing, it's most likely on the higher end of the scale, right? Missing is dependent on the respondent's income, which we don't know, and so this would be not missing at random data. Okay, so say you're sitting there and you're like, I don't know what she's talking about. Let's actually see some examples so you can maybe understand it a little bit more visually. So I'm going to bring in an example data set. It's the National Health and Nutrition Examination Survey, which is a nationally representative survey of US citizens. It's collected in 2-year cycles with these probability samples of about 5,000 people per year, and it's conducted by the National Center for Health Statistics at the CDC. These are publicly available data. You could go to that link and download the data sets and play along with me if you really wanted. It's a great resource. So for NHANES, participant age is fully observed in the data set. And so what I did was I removed about 20% of the ages so we could do this demonstration. And I removed them based on the 3 different mechanisms. So for MCAR data, I removed about 20% of those ages completely at random. I had just a random sample that I took out. For the MAR, I made it based on participant sex. So within males, about 10% are missing, and within females, about 30% are missing. So the fraction of missing information is dependent on sex. And then for the not missing at random situation, I took, again, about 20% of those ages out, but only if the age was 55 years or older. So missingness then becomes informative. It's based on age, but of course, age is the thing that's actually missing. So this was, a quick summary of the data set then. So in the observed data set, we have about 9,000 people with a mean age of about 34 with a standard deviation of 25.5. Now you can see under MCAR and MAR assumptions, those estimates don't change too much, it's okay, but wow, that's a problem with the not missing at random data. So if we just use this data set as we had it with the missing values, you can see how this would be a problem when we came time to try to make conclusions. And down here, you can just see the distribution of the data with the red color being the observed and the purple/blue is what was the missing values. So that brings me to another way that we can categorize missing data, which is ignorable versus non-ignorable. So the missing data mechanism is considered ignorable if it's MAR or MCAR, and there's a lot of statistical talk about distinctness between parameters of response and missing data mechanism. For our purposes, we can just say MAR or MCAR is ignorable. But what that means is the not missing at random, the informative missingness is not ignorable. We can't stick our head in the sand like this ostrich. We actually have to do something about it so that we end up with not biased results. So then the question is, what do we do about missing data? Well, there are a lot of approaches to handling missing data. We're going to go through these briefly all, touching first on some of the basic approaches of complete and available case analysis and weighting procedures. So with complete case analysis, we're using only the observations that have no missing data. So we would take all of our observations, all of our variables we're interested in, and if any observation was missing a value for any of those variables, it would be removed out of our data set. So this is also called list-wise deletion. This is acceptable only if the mechanism is MCAR, which is unlikely if there's a lot of missing data or a lot of variables with missing data. So an advantage of this, this is a simple and easy thing to do. And when we're looking at individual variables, doing univariate analysis, we end up with the same sample underneath. The sample isn't changing, and we're going to talk about that's a little bit different with available case analysis. Disadvantages: if we do have data that are MCAR, the biggest disadvantage is the fact that we're losing the sample, we're decreasing our sample, losing power and precision. If the data are not MCAR, we can end up with sometimes very severely biased estimates. And we can see that again with the not missing at random data set over there. If we had just continued on with our analysis as complete case analysis, we would probably have a little bit of a problem. So the next is available case analysis. So for this, we're using all of the available data for each variable. So we also call this pairwise deletion. Again, this is only acceptable if the mechanism is MCAR, and it's a very simple and easy thing to do. You're also using more data than in complete case analysis, because if you have available data for one of those variables, they would be included rather than dropping them out if they were missing something else. And we can get generally good results under MCAR. A main disadvantage to this, though, is that your sample changes from each variable. So that can be a little hard to explain, and our denominator changing can cause some problems. We still have those same disadvantages that we had with complete case, which was the loss of power under MCAR and potentially severely biased estimates if data are not MCAR. So the next approach is weighting adjustment. And if you're familiar with surveys and survey weighting, that's the type of weighting that I'm talking about. So the sample is weighted to account for the missing observations. So the observed observations can be up-weighted, down-weighted to account for those that are missing, so that you're making estimates of basically your total sample. So there's three ways that we calculate weights. We can do inverse of the probability of response, where you basically group the data together into these adjustment cells where your observed and missing seem similar, and then calculate the weight that way. You can also use a propensity score model to calculate the weight. And then sometimes if you have target population data, so you'll have like marginal totals for your population that you want to weight to, you'll see sometimes iterative proportional fitting or raking being used to create the weights so that the sample looks like the target population. So advantages for this, this is an unbiased way to analyze the data when you've correctly specified the weights and when data are MCAR or MAR. Disadvantages, though, that when you introduce weights into an analysis, you have to do specific analytical techniques to appropriately account for those. Otherwise, you just sort of wasted your time. And when you're creating those adjustment cells, like we talked about, we end up having to categorize continuous variables. You can lose some, loss of information because of that. So the next approach that we're going to talk about is single imputation methods, of which there are quite a few of them. So single imputation methods are considered sort of better than complete and available case analysis. And what you're doing basically is you're filling in a missing value with one replacement value, and then you analyze the data set as if there was no missing data. All of these methods assume MAR or MCAR. Now, the goal is it's not to recover missing data because, that's very hard to do. The goal instead is to get a valid and unbiased population estimate. Okay, so keep that in mind. And when we're talking about that, a lot of what we're talking about is getting an appropriate variance or standard deviation so that the inference that we're making is correct. So the first method is last observation carried forward. And so this is just like what it sounds. You take the last observed value and you bring it forward if data are missing. And so this is usually used for dropout from studies, right? So if you have, say, a baseline value and your patient doesn't come back for visit 1, you would just take that baseline value and move it forward. This actually used to be the method of choice for longitudinal studies, but it's falling out of favor because techniques have improved, and as they've done a little bit more work, they've realized that maybe this isn't as unbiased as we thought it was. So this is a simple and easy approach. You literally can just copy data forward. You don't have to do any fancy statistical methods. And it actually can be an acceptable way to handle missing data if what we call the response profile, if it stays constant after the participant drops out. So like if we're trying to impute age, for example, right, we know how those change and that's a constant value. But if you say looking at someone's blood pressure, we don't know if after they've dropped out, it's going to be going up or down. And so that maybe is not an acceptable use of this. So that assumption of the response profile being constant is often unrealistic. And as they've sort of gone more into this, realize that even under the MCAR situation, you can get biased results if that response changes in a way that you didn't account for, right? They often thought this was a conservative way to handle missing data, in that it was underestimating the actual effect, but the reality is you could overestimate that value if that response profile changes differently. The next is mean substitution. So I see this one pretty commonly, unfortunately. And so what you're doing here is you're filling in the missing values with either the unconditional, so the whole, total mean, or a conditional mean where say, you're taking, stratifying your data and taking the mean of a group. You can also use the median or the mode, sometimes you'll hear. There's no advantages to this method. Basically, this is not a great approach to use. You distort the underlying distribution of your data, and I'm going to show that on the next slide, like very drastically. You produce very deflated estimates of your variance, and we just shouldn't really use this method. And so to give you the understanding of why, so I went ahead and I did mean substitution for our NHANES data. And you can see that the mean isn't changing too much. Our variance, though, our standard deviation is much lower than in the real data set. And this is really the big problem. We've just introduced this huge distortion in our data set because all of the missing values are now that one value. And you can see that just causes a problem. And just to show it doesn't make it any better if you use the median, it's still the same problems. Okay, next is hot and cold deck imputation. So for this, we're substituting a randomly drawn observed value either from an external data set, which is called cold deck, or from our same data set, which is called hot deck. And so a fun little fact about the naming, it actually comes from the days of programming on punch cards. So your data set used to be on punch cards, and the external cards hadn't been run through to be read yet, and so they were so cold, hence cold deck, whereas the ones that you had just processed from your data set were hot deck. So that's where the naming comes from. So for this, we stratify our data into those similar groups like I talked about with the weighting. So our values in each group are missing and are observed are similar. And then we would select one of the values with replacement from the observed, and that's what we would use as the imputation. And interestingly enough, this is actually the method that is most commonly used in some of these large national data sets, for example, from the US Census Bureau. So those like American Community Survey data sets, for example, usually use hot deck imputation. So advantages for this is, we're using an actual observed value. So we end up with a logical value to impute. And the random draw, where you're taking that random observation to impute, does help inflate our variance, which again is a good thing because it helps us with introducing the uncertainty that we have in the imputation process so that we have correct inference. Disadvantages, though, you can lose some amount of your data because you have to categorize continuous variables to create the strata. And if you create the strata and it ends up that there is no observed value within one stratum, you can't actually impute because you don't have anything to draw from. And it can be hard to sort of understand and describe the variance when doing this imputation method, and you can end up distorting correlations. So I went ahead and did some hot deck imputation in the NHANES data, and you can see that we end up with, again, our point estimate and our standard deviation is decently okay. So I'm very close to the observed, but that doesn't help us with the not missing at random case. We still have a definitely not quite appropriate estimate there, and you can again see the distribution of the cases. Okay, next is regression and stochastic regression imputation. So for what this is basically we're creating a regression model based on the observed data, and then we predict the values and we impute those predicted values for our missing values. And when we add random error to that predicted value, we end up with stochastic regression. It seems like a real fancy statistical term, that's all it means. So some advantages. When you have data that are not normally distributed, we've been talking a lot about methods that require sort of normal distribution or something continuous variables. This actually, regression models, any regression model can be used rather, so that you can impute your missing value, whether it be continuous, categorical, following whatever type of distribution that you can think of. And the stochastic regression, because we're adding that random error, does improve our variance. So that is an advantage of that method over regression imputation alone. Disadvantages, well, like any regression model, we have to correctly specify our model, and we have to have good predictors so that we can get a good predicted value. When we have the non-stochastic regression, the predicted values will all fall on the predicted line, which is a little bit of a disadvantage, which is why stochastic regression does help improve that. And when we have more than one variable that's missing and it's in a non-monotone pattern, we have to decide which one are we going to impute first, right? That's a big decision, and you would use those imputed values then further on in the next imputation, and so that could be a problem. The biggest disadvantage of this method, though, is that the predicted value can be outside of a logical range. This is based on a prediction off of a regression model, and you can end up with, a negative age, for example. So that is the biggest downside for this. So I created a regression model with gender and marital status being the two predictors that I just picked sort of at random for the NHANES data, and predicted the values using just a regular regression model, linear regression model. And you can see that the mean and standard deviation for MCAR and MAR are pretty good. We're getting a little bit of a better estimate for the NMAR situation, probably because the age and marital status variables might be correlated. And so we end up getting slightly better estimates than previously. And you can see that the distribution's, it's okay. There's generally good match. However, for the stochastic regression, where we're, again, it's the same imputation model, but now adding random error to the prediction. And this is the problem. We can end up with these negative values, or some of these predictions were, over 100, which is potentially not the correct, well, probably not the correct answer at all. However, we see that on the population level, our actual parameter estimate is pretty close. Okay, the next one is dummy variable adjustment. This is also sometimes called the missing indicator method or use of a proxy variable. And what we're talking about for this is missing values in nominal or categorical variables, where we take the missing values and all sort of group them together and treat them as their own category. Now, you could say that you'd also do this with continuous variables, where you would set it all to a constant. The constant is typically mean, and therefore it's really just analogous to mean substitution. So there's some advantages to this method when we have a situation where the data are missing on purpose. So say, you're asking about someone's spouse and they're not married. So that question didn't apply. This is actually can be an acceptable way to handle the missing data. If the data are actually truly missing, however, you end up, creating these biased estimates, even under MCAR, because you think about like the heterogeneity in the people who are missing, if we just group them all together, that's not necessarily the most valid way to do this. Okay, the next is predictive mean matching, which is sort of marrying the concepts of regression imputation and hot deck together. And in fact, it's called regression hot deck. So what we do is we create a regression model based on the observed data, where we then predict the value for both observed and missing cases. And then that predicted value for both of those, of the missing, is matched to the closest predicted value from an observed case called a donor case. And we either do the matching one-to-one, or you do one-to-many. Then we use, instead of the predicted value, we use the observed value to impute that missing value. So the donor's observed value is the imputed value for the missing value. And if we did a one-to-many match, we select the donor at random. So an advantage of this is that it gets around that problem with the regression imputation, where you can get illogical values, and instead you end up with using an actual observed value. So that makes it a little bit better, right? Disadvantages are that we again it's a regression model. We have to specify our model correctly, and you can end up with too few donors sometimes, either because you don't have enough observed data, or if it's a one-to-one match. And in the case of too few donors, you end up selecting them again repeatedly, and that can impact your variance. So I implemented predictive mean matching within the NHANES data set, and you can see that our parameter estimate and our standard deviation are pretty good under the MCAR and MAR situations. Not bad, not great though, for not missing at random. So again, we're getting over a little bit of the problem of not missing at random, but that would still be considered probably a biased estimate. You see the distribution of the data matches pretty well. Okay, those were the single imputation methods. Now we're going to jump into multiple imputation, which really is becoming the gold standard for how we handle missing data. So it's considered a better approach than complete or available case analysis and single imputation methods. And so basically what we're doing, multiple imputation, as it sort of sounds, we're filling in the missing value with more than one replacement value, so two or more. And all of these methods for multiple imputation, again, require the assumption of MAR or MCAR. So like we talked about, the goal is not to get the value that's missing, not to recover that, but again, to get this valid and unbiased population estimate. All right, so let's talk about the process of multiple imputation. So multiple imputation occurs in 3 steps, although sometimes the last 2 are grouped together in just called the analysis step. And so what we're doing is we're going to fill in the missing value with 2 or more replacement values that are drawn at random from any distribution, an appropriate distribution. So we create basically M copies of our data set, M being the number of imputations that we are conducting, where in each of those data sets, you have the same observed values and then different imputed values. And so the variability that we have across those M data sets reflects the uncertainty that we have in the imputation, which is how we get those valid estimates. And so to see it graphically, so if we start with our data set with missingness, in our imputation step, what we're doing, again, we're like copying that data set over and over and imputing in those 1 to M data sets, different values. In the estimation step, each of those imputed data sets are then analyzed as if it was a separate data set using complete case methods. And then in the pooling step, we take the results of each of those 1 to M estimates and we pool them together using something called Rubin's rules. So Donald Rubin in the 70s came up with these rules of how to pool the estimates, and it's just continued on, and now we just call them Rubin's rules. And we'll talk about how we do that right now. So some key points for multiple imputation. So that M, the number of imputations, it used to be that people would say 5 to 10 was sufficient. We have better computational power. And so now sometimes you'll see closer to 25 or even 50 or more. And a lot of times people say the number of imputations you do should be based off of the amount of missingness in your data. That's not a hard and fast rule. There's some sort of nuance to the decision of how many imputations you should do. When we're generating the imputations, we do it in something called the Bayesian framework. So the Bayesian approach allows for the introduction, we use it as a random variable, it's called. And so we can introduce uncertainty in our estimate. And that's the key thing. So we have that appropriate inference, right? So we're not doing single imputation over and over. Instead, we're drawing a random value following this framework. And then in terms of the pooling, so for the parameter estimate, the pooled parameter estimate is the mean of those M estimates, and then the pooled variance, this is the only formula in the whole thing, I promise. It accounts for the variance both within the imputation and then between those imputation data sets so that we can reflect that uncertainty appropriately. So there's 2 main methods that we talk about with multiple imputation. The first is multivariate normal imputation. And so that's actually the first method that was described. It used to be the only thing that we had, in fact. And what this does is it uses this Markov chain Monte Carlo MCMC simulation that's called data augmentation to impute the data. So again, we're using this distribution that is based off of a prior distribution that you specify, and then the observed data distribution, and that's where a value then is drawn from. So it used to be this was the only option that we had, and so there were some sort of tricks and workarounds so that you could impute non-continuous data, because multivariate normal implies that your data are normal and continuous. Now, you can do that. It's not ideal because now there's this newer method called multiple imputation using chained equations, or MICE, or also called fully conditional specification. If you're a Stata user, the MICE is sort of the term that is preferred. And if you use SAS, they call it FCS. So what's happening with this is that you're doing a sequence of univariate imputations. So not single imputation, univariate just being one variable at a time. So you do the sequence of univariate imputations where you're specifying each of the prediction equations. And so because you can specify the equation, it can handle any type of data. So you can use You can use a linear regression model, you can use a logistic regression, a Poisson regression, you can, whatever equation you want to fit, you can use within reason. And therefore you can handle different types of data. And in fact, you can handle multiple different types of data within the same imputation. So just as an example, pulling from the Stata reference manual on multiple imputations, you can see some of the methods that, at least are implementable in Stata. I'm a Stata user. It's broken down by whether you're doing a single variable univariate imputation versus multivariate imputation. And then what you can do, the method you can choose, is based off of the pattern of the data, the type of data that you have, and then these are the options that you can choose from. So going back to our NHANES data, what I did was a imputation using the multivariate normal approach, MVN, where I did 5 imputations just so that you could visually see 5 of them. And then you can see now we're talking about standard errors rather than standard deviations, but our estimate is really quite close under the MCAR and MAR situations. It's not any better with not missing at random. So multiple imputation does not fix, does not resolve the issues of data not missing at random. And you can see that we have a standard error that's very similar or slightly inflated, which is pretty common with multiple imputation. And down here, you can just see the distributions. So again, there's 5 different data sets. And so this is a distribution of the data for each of those 5. Okay, that was a very, very brief overview of multiple imputation. We could talk about that probably for at least an hour. And so now we're going to jump into the last 2 model-based approaches, and then touch briefly on how we handle not missing at random data. So the first model-based approach is using something called the maximum likelihood estimation. And so for this, we have to have MAR or MCAR data again, and it has to be in a monotonic missing data pattern. We also have to have or require the assumption of normality for our data. And it's a computationally intensive process and harder to implement. And so these are really not as common in the clinical research setting. Maximum likelihood approaches are more commonly used like in behavioral sciences and psychology. But they're kind of growing, I suppose, in use for clinical research. So there's 2 main approaches that we talk about: full information, maximum likelihood, or sometimes we call this direct maximum likelihood estimation. So instead of imputing, we're using something called the maximum likelihood function to estimate the population parameter, and we're using basically all of the observed data that we have and fitting this model. There's a disadvantage to this. It's very hard to implement. Because of all of the assumptions that we have to meet in terms of MAR or MCAR and normality, it's not really a commonly used one. The next is the expectation maximization, or EM, algorithm. And so for this, it's an iterative 2-step algorithm where you first impute with some value, an expected value that's based off of your observed data. You find if that's the maximum likelihood estimate, and if it's not, then you do a different imputation using more, as you go through this process, and then you repeat over and over until it converges, convergence being that your estimate doesn't change very much. This is not particularly used as well now that we have multiple imputation, and a disadvantage of this is that we underestimate the variance in doing the EM algorithm. And the next is weighted GEE. So if you are familiar with GEE, it's called generalized estimating equation. This is sort of an extension of those different models. And so this is used mostly for longitudinal studies, because we have to have that monotonic missing data pattern, right? Where if we look over time, sort of we have more and more missing. And so there's 2 steps to weighted GEE. First, you estimate the probability of dropout or probability of missingness using or creating an inverse probability weight. And then we fit a GE with those weights, and we get this weighted GE that can handle those missing data. All right, finally, not missing at random methods. So when we have a mechanism where data are missing, not at random, it's non-ignorable or informative missingness, there's not a bunch that we can do because those missing data are we needed them, right, to make those estimates. And so what we end up having to do is sensitivity analyses using these methods. And so if you're not familiar with the sensitivity analysis, it's sort of the epidemiologist's way to say, what if? So we examine different scenarios to see, what if our imputed data are off by some factor. So we've imputed our data, but we realize that, okay, maybe it's like a little bit more this way or a little bit more that way. And so that's where a lot of these methods are handy and can come in useful. So there's two common methods that you'll hear. A selection model where we're using the latent variable. So again, latent variable means it's unobserved. We're inferring it from our data. So we use a latent variable to model the missing data mechanism. Or a pattern mixture model where we're basically modeling the distribution of the response as a mixture of the distribution of our observed data and the distribution of the missing responses that we are hypothesizing we think they could look like. So again, these are pretty advanced methods that are very handy to make sure that the assumptions we're making in terms of the mechanism is appropriate, so we can see, well, how bad would it be, I guess, if our data were not missing at random, how off could we be? Okay, so that was a very brief overview of a lot of different methods that we can use to handle missing data beyond sort of this default of complete case analysis. So the method that you choose really depends on, the type of data you have, the mechanism of missingness, the pattern of the missing values, and the goals of your analysis. But regardless of how you choose to decide or how you decide to handle missing data, there are some key details that we should include when we're discussing our results and methods. And so things that we need to report on, we really need to say how much missingness did we have? So what was the number of missing values for each of our variables of interest? What are some reasons for missing data? Did you introduce missing data on purpose, for example? That would be an important thing to report on. And if you made exclusions based on missing data, say, you excluded any participant that didn't have the outcome measured, that's very important. And we should also think about how that exclusion impacts our results in terms of selection bias. And then finally, you should state the mechanism, your assumption of the mechanism of missingness. We should also think about assessing for differences between the complete and incomplete observation. Again, that's getting at the potential for selection bias if we are excluding those people that are missing, or it also gives us sometimes a little bit of a hint of, are these data maybe not missing at random? And then any method that you use, whichever one it is, it's really important to report the approach that you use and key details about that. If you are imputing, you should, talk about the type of imputation you did, the number of imputations, that kind of thing. So to summarize, I hope you now understand that, missing data is common. It's going to happen in clinical research. The important thing, though, is to understand that how we handle missing data really can affect our results. And some methods, mean substitution, for example, might be commonly used, but they're probably not the best choice. And no matter what we choose of how we handle these, we should be transparent about the missing data in our work. It can affect the validity of our studies. And so we need to report on those key details, the key aspects of how we handle the missing data, so that not only our peer reviewers, but also readers can understand the impact of missing data on our work. So I'd like to thank SAEM for the opportunity to talk with you today, and I'd be happy to take any questions now, or please feel free to reach out to me in the future.
All right. Well, thank you so much, Dr. Cash, for this very informative presentation. And thank you to everyone watching this webinar for the SAM Research Learning Series. Have a great day.